All right, so we just got a couple more examples that we're going to work through in this problem set to drive the point home. So this proton spectrum here is actually from a compound that we've synthesized in my own labs. So we've been studying this particular heterocycle for a long time. And so this is an actual experimental NMR, so you can see a few things that make it look like a not so pristine as some of the other ones that we have. There's some other little fuzzy peaks that correspond to small amounts of contaminants and stuff in the sample. So this is more realistic of what you would be looking at in a real spectrum. All right, so if we look at this structure in terms of the signals we would expect, first signal we would think about seeing is this methyl group directly attached to sulfur. We can call that signal A. This N-butyl group, that's a 4-carbon chain, so hanging directly off of that carbon-carbon double bond in that 4-membered ring is going to be this 4-carbon chain. That's a linear alkyl chain. We can label those pieces directly attached here. We can call this one signal B, C, D, and E. And then the final set of signals we would expect would be the 5 hydrogens that sit on this phenyl ring, which is that benzene, right? So that's signal F. So as far as nailing down signals, if we look at probably the easiest one to nail down first is going to be this signal F that corresponds to the 5 hydrogens on that benzene ring. Again, we're going to expect that to be in that range of 6.5 to 8. You can see I see this multiplet here of peaks right around, I guess 7.8 or so, 7.5. And you can see based on the integral 4.84, so that's about 5. I'm seeing 5 protons in that region between 6.5 to 8. So that signal corresponds to all 5 of the hydrogens on that benzene ring. So I can nail that down as F. And again, that phenyl is going to be this, where all 5 of those hydrogens on that system are going to resonate at that same spot. All right, next up we've got the next easiest one to pick out is going to be signal A that sits on the sulfur. So we would expect it to be relatively far downfield because it's attached to a heteroatom, so it should be in that range of 2 to 4, 2.5 to 4. Because that CH3 doesn't have any neighbors on the neighboring atom, we're going to expect it to be a singlet, right? And so the only singlet that we have in the spectrum is here, so this corresponds to A. And then the remaining signals are going to correspond to this alkyl chain on the N-butyl section, and we'll see the chemical shift of each of those signals B, C, D, and E. They'll decrease as we get farther away from that carbon-carbon double bond. So that means that B should have the farthest chemical shift, followed by C, then D, and then E. If we clue in on splitting patterns, B, one signal for that CH2 plus its 2 neighbors, that should be a triplet. If I look at C, one signal for those 2 hydrogens plus 2 neighbors on the left and 2 neighbors on the right, so that's going to be a quintet, so a series of 5 peaks. Signal D. D has one signal for those 2 hydrogens plus 3 neighbors on the left and 2 neighbors on the right. So that's going to be a sextet, so it would be a series of 6 little peaks. And then signal E, one signal for those 3 hydrogens plus its 2 neighbors. I would expect that to show up as a triplet. And remember, as far as chemical shift goes, we were going to expect that chemical shift to decrease as we go from B to C to D to E. So if I look at the remaining signals, I should be able to pin these down pretty easily, right? So the farthest downfield signal that I have is this triplet, about 2.2 or so, 2.5 or so, something like that. It's a triplet. That corresponds to signal B. The next 2 multiplets that we have are in this range between, say, 1 and 2. They both integrate to 2. The closest one to the heterocycle is going to be signal C. That should be a quintet. We can call this signal C, which means the multiplet here next to it is going to be D. And then E should be a triplet. The remaining signal here is a triplet, so I can assign that one as E. So it's not super hard to knock down all of the signals in that alkyl chain just by keeping in mind that the chemical shift's going to decrease as we go farther away from the site of attachment, which is that position next to the carbon-carbon double bond, and then we can follow the splitting pattern all the way home. All right. Next example is going to be this linear alcohol with a bromine attached to it. And so this one, I think, on some level is a little bit easier than some of the ones we've looked at previously. So let's look at the signals that we would expect in this case. So the first one that we have is the hydrogen directly attached to the alcohol. That should be A. And we have the CH2 that holds the alcohol, B. Another CH2C, which is different than this CH2D, CH2E, and CH2F. So we got a whole bunch of CH2s in this system that we have to nail down. But thankfully we can rely on splitting patterns here to think about what each should look like. So starting with signal A, that hydrogen on the oxygen, remember it's exchangeable, so it doesn't feel any neighbors, so that's going to be a singlet. Is going to be, in fact, the only singlet in the system. So I can already go ahead and assign the one singlet in the spectrum to A. So that takes care of that peak. Next thing I would do in this spectrum is take a look at the two series of hydrogens that should be farthest downfield. The two candidates for farthest downfield are going to be B, carbon attached to an OH, and F, carbon attached to a bromine. If we look at their expected splitting patterns, B has two neighbors, so B should be a triplet. F also has two neighbors, it should also be a triplet. And so if I look in the spectrum, we've got two triplets here between 3 and 4. That's consistent with those hydrogens being on a carbon next to those electronegative atoms. Bromine's more electronegative than oxygen, so I would expect the farthest downfield peak to correspond to F, triplet. The next farthest downfield peak should be B, a triplet attached to the oxygen. Okay? So then all that remains in this is going to be 3 signals that we have here that correspond to CH2s that we haven't assigned. Right? So we have CH. We've got carbon C, D, and E, each of which having, each of them having hydrogens. So if I think about E, E should be the one that's farthest downfield because it's the nearest of those 3 to the most electronegative atom in the system. So I would expect this signal to be E. If I think about its splitting pattern, it should be complex because E has 2 neighbors on the right and 2 neighbors on the left. I would expect it to be a pentet, and that's consistent with what we see there at that farthest downfield system. The next farthest downfield one should be C, since it's close to the oxygen, closer to the oxygen than D. C should also be similarly complex. It should be split into a series of 5 peaks because it has 4 neighbors. So I can assign that one as C, and then by process of elimination, that additional peak should be D, which is going to be sort of a more complex splitting pattern because we have, again, 4 neighbors in that system. So that's how we can nail down each of those peaks in this particular one. So again, here we're relying on a combination of chemical shift and splitting to figure out the assignments. All right, last one that we're going to talk about. Another case where, again, we're going to have to rely on a combination of chemical shift and splitting patterns to think about nailing down the individual assignments. So, again, first effort is going to be pointing out how many independent signals we have. I only have one methyl group in this system, so it's going to be chemically distinct from all the other signals. CH2 here directly attached to the methyl is different from this CH2 on the other side of the oxygen. This CH2 in the middle of the chain is going to be chemically distinct from the CH2 holding this oxygen. and then the hydrogen directly attached to that OHF is going to be distinct from all the others. So if we want to think about starting to make assignments, again, we're going to clue into the fact that hydrogen on OH is exchangeable. It's always going to be a singlet. Typically will be broad because of the fact that oxygen can exchange and engage in hydrogen bonding and all sorts of things in solution. And so the singlet here right at 3, that's going to correspond to F, broad singlet at 3. So I can take that one off the list. Now let's take a look at chemical shift. We've got really 3 signals that should have similar chemical shifts. So I've got 3 signals that should fall in this range between 2.5 to 4.5 because they're directly attached to a heteroatom. And so those signals turn out to be signal B, C, and E. And so we should be able to see some things about, say some things about each of those peaks in terms of where we would expect them to come. So they're all going to be in that range of between 3 and 4. So these 3 signals are here. Now we need to see if we can understand a little bit about splitting to nail down each one. The easiest one to nail down is going to be B, right? Because B has 3 neighbors. I'm going to expect B to show up as a quartet. So only one of these 3 signals in this region is a quartet. It's the one that's farthest upfield, so I can assign that signal to B. And then I've got these 2 triplets that I have to parse out, and it turns out it's not super easy to tell which one is which, to be honest. E next to the oxygen of the OH typically is going to be the one farthest downfield. It should be a triplet because it has 2 neighbors at D. So we can go ahead and guess that one might be E. And then we can say that the other CH2 next to that oxygen, which also should be a triplet, would be C. It might not be. It could be that those 2 we have switched, but we would have to verify that by another perhaps carbon NMR experiment to actually nail down each of those 2. All right, the final 2 signals are these 2 here in that range of 1 to 2. We've got one that's a complex multiplet and then one that is a triplet. That triplet is going to be A, because remember we would expect A to be a triplet by virtue of its 2 neighbors at B. So we can assign that triplet A. And then this multiplet then by process of elimination should be D. And we can ask ourselves, does it make sense for D to be heavily split? D has 2 neighbors on its left and 2 neighbors on its right, so we would expect D to originate as a quintet, and that's exactly what we see in the spectrum. All right, so that's been a series of examples of sort of how you can move through an NMR spectrum systematically, taking advantage of those 3 pieces of information that we have: chemical shift, expected splitting pattern, and integration. And that way we can go through and actually look at assigning each individual peak in the NMR.